A combination of hydrogen peroxide and UV light could be applied for the advanced oxidation process. In this process, hydrogen peroxide is added ahead of UV irradiation to the water, so hydrogen peroxide treated water is irradiated with the UV light, and it's going to proceed with generation of hydroxyl radicals, which I mentioned earlier. They are so reactive and they can destroy the wide range of synthetic organic compounds that are present in some of the water supply. As you see here, the oxidation potential for hydroxyl radical is 2.8 volt, which is greater than ozone and chlorine, which are the conventional oxidants used for disinfection of water. And the advantage of this process is that it's not selective and it's effective for a wide range of organic contaminants present in the water. We have several chemical reactions during the hydrogen peroxide UV irradiation oxidation process. So basically this is the two-step chemical oxidation process. At the first step, hydrogen peroxide is converted to the hydroxyl radicals. UV irradiation catalyzes the hydrogen peroxide dissociation into the hydroxyl radicals. We have other type of chemical reactions happening in the process as well. So first step was generation of hydroxyl radicals. Hydroxyl radicals are so reactive and they are going to attack the synthetic organic compound which are present in the water. So the radicals are going to obstruct hydrogen atom from the organic material. So they are going to obstruct the hydrogen atom, forming water and forming the organic radicals. This organic radical is going to pursue further oxidation reactions. So as I mentioned, we had the two-step chemical oxidation process. At the first step, hydrogen peroxide was converted to the hydroxyl radicals and UV irradiation catalyzing that process. At the second step, hydroxyl radicals are going to attack the organic contaminant present in the water and obstruct the hydrogen atom from them, forming the water and organic radicals. So basically they are forming several byproducts. So we can calculate the rate, the chemical reaction rate for this process. So we have the rate law for hydroxyl radicals that are reacting with the organic compound. So in this process, we have the destruction rate of organic compound with hydroxyl radicals. The unit is mole per liter second. And then we have the second order rate constant for destruction of organics with hydroxyl radicals. The unit is liter per mole second. We need to have the concentration of hydroxyl radicals, mole per liter, and concentration of target organic contaminant, which is mole per liter. So when we are conducting the calculation and we want to calculate the destruction rate, we need to make sure that we have the right units. For example, if we have concentration in milligram per liter or microgram per liter, we need to use the molecular weight and convert those to mole per liter. So I mentioned here that we need the concentration of hydroxyl radicals. The concentration of hydroxyl radicals generally varies between 10 to the minus 11 to 10 to the minus 9 mole per liter. So if we have a problem and we want to solve the problem, it's generally given the concentration of hydroxyl radicals. We can calculate the half-life for the target organic compound. So basically the half-life is defined as the time that required the organic contaminant concentration reduced to half of its initial concentration. And as you see, this is the function of hydroxyl radical concentration. So if we have the higher concentration of hydroxyl radicals, the half-life would be shorter, so the reaction would be much faster. So in shorter period of time, we are going to reach the half concentration of organic compound. So in this table, you see the second order rate oxidation reaction constant for degradation of selected inorganic and organic species by hydroxyl radicals. So these are inorganics, organics. We have the hydroxyl rate constant, and we have different concentration of hydroxyl radicals, 10 to the minus 9 molar, 10 to the minus 10 molar, and 10 to the minus 11 molar. And these are the half-life. So for example, if we consider degradation and destruction of ammonia by hydroxyl radicals, we have the rate constant 9 multiplied 10 to the 7. And you see when we have a higher concentration of hydroxyl radical, 10 to the minus 9 greater than 10 to the minus 11, the half-life is much shorter. So if we have concentration of hydroxyl radicals as 10 to the minus 9 molar, the half-life would be only 0.13 minutes. But when we have lower concentration of hydroxyl radicals, 10 to the minus 11 molar, we need to have 13 minutes to reach the half-life for ammonia destruction by hydroxyl radicals. So you see that how half-life is different for some of them, like benzene or atrazine. The kinetic of reaction is pretty fast, so the half-life is very short. So for most of these, the half-life is in the range of minutes, less than even less than 2 minutes when we have higher concentration of hydroxyl radicals. So the process is very fast and could be very effective.